Hi everyone, my name is Vicky Fawcett and I'm a PhD student at Durham University, and today I'm going to talk a bit about my work looking at an Xshoot insight into dust reddened quasars. So just a brief bit of background, quasars, also known as QSOs, are extremely luminous types of active galactic nuclei, and the majority of the quasar population have very blue optical colours, and this is typically due to an unobscured view of the accreting supermassive black hole. However, we've recently found an important fraction that are red at optical wavelengths, and we refer to these as red quasars or RQSOs. So the red colours typically indicate that the accretion disk is obscured by a column of dust, but whether this is due to an inclined dusty torus or a phase in the evolution of quasars has been widely debated. So these are the two most popular scenarios. On the left is the orientation model, and you can see this classic schematic of the unified model of AGN. And here, a blue quasar would have this unobscured view to the accretion disk. And then you could imagine a red quasar having this grazing angle through the dusty torus. So in this case, a red quasar is nothing more than just an inclined blue quasar. On the right is the evolutionary scenario. And in this case, a red quasar may represent an important phase in galaxy evolution. So this little comic strip was taken from a press release following a former PhD student at Durham, Lizelka Klint's 2019 paper. And this is just one of the models that you could imagine where a red quasar could be in a younger phase and then evolve into a blue quasar. So our work's been really interested in trying to distinguish between these two scenarios. So there's many groups that look at these reddened quasars, but we believe we've got a consistent selection of red quasars because we also select a control sample in a similar fashion so that we can compare our results. So for all of our work, we use Sloan Digital Sky Survey quasars. These are optically selected. And then for the parent samples, we restrict to a redshift range of 0.2 to 2.4. We then select our red quasars as the top 10% of the G-I color distribution, and then select a typical or control sample as the middle 50%. And I'll refer to these as either control or blue quasars. And we do this selection in a redshift dependent manner, as you can see by this figure. So why are we interested in red quasars? Well, I briefly mentioned Lizelka Klint 2019 paper, and in that, she found fundamental differences in the first radio properties of SDSS red quasars. First being a radio survey at 1.4 gigahertz and 5 arc-second resolution. So I'll just summarize the three key results from her paper. First of all, we find a factor 3 higher radio detection rate in the red quasars compared to the blue. We find this enhancement arises around the radio quiet threshold, but when you look at the radio loud systems, we find this enhancement disappears. And finally, if you look at the radio morphologies, we find that red quasars prefer faint or compact, so unresolved radio counterparts. But if you look at the more classical, extended or double lobe systems, we don't find any difference between the red and the blue. These results were really exciting because they rule out the simple orientation model alone, and they suggest there's something more fundamentally different about red quasars. So red quasars are not just normal blue quasars seen edge on. Since then, we've had a bunch of papers out. They've mainly been looking at following up on these radio results that we've seen. We've also looked at SED fitting, X-rays, and also ALMA data. But there's still questions there that remain. For example, is dust the cause of the red colors? If it is, then what's the location and the nature of this dust? And finally, are the accretion disk properties different in red quasars? Because this could be one of the driving factors for the reason why we see the difference in the radio. So this is what I hope to answer in my latest project, which is using an Xshooter sample of red and blue quasars. So for those that are unfamiliar, Xshoot is a multi-wavelength medium resolution spectrograph on the VLT, And it provides spectra with a continuous wavelength coverage from 3,000 to 25,000 observed angstrom. So this is really wide wavelength spectra. It's really great data. So I'll go straight in with the data that we have. So the top plot shows 13 control quasars that we observed, plus 15 archival sources from Capilupo 2015, normalized at H alpha, and then overlaid in the darker color is the composite. On the bottom is the 12 red quasars we've observed, again, normalized at H alpha. And for this sample, we restricted it to a redshift range of 1.45 to 1.65. And this was to ensure that we observed the H alpha in the near infrared band, but also to match the archival sample. So for those that are unfamiliar with quasar spectra, the top is kind of a typical quasar spectrum. You can see the broad lines, especially the H alpha, which is very bright, and also narrow lines such as the O3 that are studied. So directly comparing the two composites we have, and again, normalizing to H alpha, what's immediately clear is that the red composite appears to be consistent with the control plus some amount of dust reddening that causes this difference in the shape. You can also see that, as expected from a dust reddened system, the optical lines are more diminished in the red composite. So the first bit of analysis I look at is to robustly test whether dust is the cause of these red colors. So to do this, we test different extinction curves. So we take the control composite and add different amounts of dust to see if we can fit the red quasars. And we also want to see if there's a preference for a particular extinction curve, because this would tell us something about the nature of the dust. So we test a simple power law, an SMC, a steeper and a flatter curve. So this movie describes it a little bit better. So the cyan line is the control composite, and then this black moving line is the control composite plus an amount of dust, which is shown in the bottom right here, and then overlaid are red quasars. And what you can see is that by simply taking the control composite and adding moderate amounts of dust, we can actually recreate the majority of our red quasars very well. And this indicates that dust is the cause of the red colors in the majority of our red quasars. We didn't find a single extinction curve that was the best fit, but we found the simple power law provided slightly better fits. But something I'm following up on at the moment is a tentative evidence that the more extreme red quasars prefer a steeper curve compared to the more moderate. But this is quite tentative at the moment. So next thing we do is we fit all of our spectra. So I don't have time to go into our fitting procedure, but I'm happy to talk about this after the talk. And from this, we fit the broad emission lines, which we can then use to estimate the black hole mass. And for this, we use the Viral black hole mass estimators from Shen and Liu 2012, the equation shown in the bottom here. And then we use the H alpha four-width half mass and luminosity. And that's because since we're looking at reddened quasars, the H alpha line is the least affected by extinction, so it should be the most robust estimator. So this graph here shows the black hole mass versus the Eddington ratio for our red and control. And what you can see is that we find that the red quasars tend to have more massive black holes. And even when we account for any biases in luminosity in our sample, we still have this result. However, we do have quite small samples, so we have actually just put in another Xshoot proposal to try and expand our sample to really tie down this result. The last bit of analysis we do is comparing the accretion properties between the red and the blue. And to do this, we just fit a simple thin accretion model, it's the Sloan and Netzer model, to both of our samples. We fix the black hole mass that we estimate from the H alpha line, and we fix extinction, which we get from our extinction curve analysis. And then we then leave spin and mass accretion rate as free parameters. And what we find is the majority of both the red and the control sample can actually be fit very well with just a simple thin accretion disk. And this suggests there's no significant differences in the accretion properties. Even comparing the best fit, spin, and mass accretion rate parameters, we don't really find any difference between the two samples. So therefore, the accretion properties are not what are driving the differences in the radio results. So there must be other AGN mechanisms at place, and something we're looking into that's looking like a likely candidate is outflows or winds. So the conclusion from this bit of work is that we find dust is the main cause of reddening in our red quasars. We find red quasars potentially host more massive black holes, but don't find any significant differences in the accretion properties between red and typical quasars, suggesting there should be something else that are causing these special properties, such as wind. So for my future work, I'll be exploring the RV parameter. RV is AV over EB minus V, and it tells you about the nature of the dust. So we're going to test whether this is different in the red quasars compared to the control, and then even within the red, like I mentioned, the most extreme reddened quasars compared to the more moderate reddened. We're also going to search for these outflows. So in a recent paper by Gabby Calistro Rivera, she found larger full width half mass of the O3 components in the red quasars compared to a control sample. And in our work, again, it's a little bit tentative at the moment, we do find that a higher number of the red quasars are better fit with an O3 wing component, which is indicative of outflows. We also find red quasars have larger carbon 4 blue shifts, but our sample's too small to really tie this down. We also find a really interesting link between broad absorption line quasars and red quasars. So for those that are unfamiliar, bulk QSOs are just quasars with known to host very powerful outflows. So again, it's very interesting that we're seeing this link between red quasars and bulk QSOs. And finally, in the last couple of minutes I have, I'll just briefly mention that I'm part of desi, the dark energy spectroscopic instrument. And I know there was a pre-recorded talk on this as well. And within desi, I have a secondary target program that's targeting these dust-obscured quasars. So the hope is to build a sample of desi red quasars that would have been missed by the main selection. So I'll just show you a couple of examples from desi because we've got really exciting data at the moment, and my program's been implemented in February this year, so we've already got quite a good sample. So the top here is a desi blue quasar. You can see this is an optical image that it's got a very blue point source. And down here is one of my red quasars. So you can see the very red continuum, but you still see these broad lines, and in the optical image, it appears very red. So we hope to do a lot of future analysis on a larger sample of desi red quasars. An exciting thing about desi is that it should push to more reddened systems than SDSS can select. So we can test some of these differences by pushing to higher AV systems. And finally, the really great thing about desi is there's now a 10-year baseline between SDSS and desi. So we can look for what we call color changing quasars, which are similar to changing look quasars. But what we're really interested in is if a quasar can become more blue or more red over time, which would tie into the evolutionary scenario. So just really quickly, this is one example we find. The black is SDSS, the magenta is desi, and then this gray line is the dust difference between the two. And we find that a dust difference of 0.2 mags can actually describe this change very well. So over 10 years, we think that this quasar's become 0.2 magnitudes bluer. And I will just leave up my future work slide. Thank you.